Hey fellow nerds, today we will solve all the gate problems on BJT circuits from 2015 to 2024. Here is our first problem. For the BJT in the amplifier shown below, VBE is 0.7 volt. KT by Q is 26 millivolt, that is our thermal voltage. Assume that the BJT output resistance is very high, which means we can ignore the early effect. Also, the base current is negligible. That means IE will be equal to IC. It is also given that the capacitors are assumed to be short-circuited at the signal frequencies. The input VI is direct coupled. That means we don't have a capacitor over here. What we have to find out is the low frequency gain. First of all, what we have over here is a common emitter amplifier. It has emitter degeneration, but we also have a bypass capacitor. Load resistor is included. So its gain is going to be minus GM RC parallel to RL. We already have the values of RC and RL. What we need is the value of the transconductance GM. We know GM is IC by VT. VT is given in the question, it is 26 millivolt. So finally, it all comes to finding the value of IC. IC is the bias current. So to find that, we have to do the bias analysis or DC analysis. To do the DC analysis, we have to switch off the input, which is AC. If I do that, the base will directly become grounded. Also, since all the signals are DC, both capacitors can be considered as open circuits. So to do the DC analysis, this is how our circuit model will look like. Since we remove the input signal, base is directly grounded. Capacitor CE is open circuited, so I do not have it here anymore. When C1 got open circuited, we basically don't have any connection between these 2 points, so I simply removed RL also. Now, let us apply Kirchhoff's voltage law in the base emitter loop, which is this one. I'll start from this point and go clockwise. As I go on, first I have the base emitter junction. So we'll have a potential drop there that is equal to VBE. As I further go on, I have RE through which a current IE will be flowing. So the potential drop across RE is IERE. And finally, I have a minus 10 volt. Now, VBE is from positive to negative. Current IE is flowing like this. That means potential across RE is from positive to negative. But then what I have over here is minus 10. So I can write VBE plus IERE minus 10 is equal to 0. Now VBE is 0.7 volt. RE is 20 kilo ohm. From this equation, we can write IE is 10 minus VBE divided by RE. Let us substitute the values. Now this is equal to 0.465 milliampere. In the question, it is given that the base current is negligible, which means the emitter current and collector current are the same. So the collector current is also going to be 0.465 milliampere. Now we have everything we need to find the gain. Like I already said, what we have here is a common emitter amplifier. It has emitter degeneration, but it also has a bypass capacitor. So the emitter degeneration will not affect the gain. Usually we write the gain as minus GM RC, but here RL is also included. So if you draw the small signal model, RL will be there in parallel with RC. So the equivalent resistance we have at the collector in this case will be RC parallel to RL. So our gain will be minus GM RC parallel to RL. Now GM is given by IC by VT. IC is 0.465 milliampere, VT is 26 millivolt. We need RC parallel to RL. RC is 10 kilo ohm, RL is also 10 kilo ohm. So the equivalent resistance when these two are in parallel is 5 kilo ohm. If we do the calculation, we get that the gain is negative 89.42. And that is our final answer. Let us see the next problem. For the DC analysis of a common emitter amplifier, neglect the base current and assume that the emitter and collector current are equal. It is given that threshold voltage is 25 millivolt, base emitter voltage is 0.7 volt, and R0 is practically infinite, which means we do not have to include early effect. Now, what we have to find out is the magnitude of the midband voltage gain. Again, what we have is a common emitter amplifier. It does have emitter degeneration, but it also has a bypass capacitor. Load resistance is also included. So the gain will be negative GM RC parallel to RL. RC is given in the question, RL is also given. Again, the only thing we have to find out is the value of IC. From the figure, we can see that a voltage divider bias is being used. So let us see what is the voltage we get at the base due to the voltage divider. It is easy to find because all we have to do is voltage division. 12 volt is being applied. It is divided between a 73 kilo ohm and a 47 kilo ohm. Out of that, whatever is dropped across the 47 kilo ohm is the potential we have over here, VB. So VB is 12 divided by 73 plus 47 multiplied by 47. This is equal to 4.7 volt. Now, let us apply Kirchhoff's voltage law in the base emitter loop, which is this one. I'll start from the ground. There is R2. There is the base emitter junction. And I have RE. Going back to the ground. I'll start from this point and go clockwise. This is basically ground. As I go, I can see the resistor R2, which is the 47 kilo ohm. We already found the potential across it is VB, which is 4.7 volt. As I go on further, I have the base emitter junction, across which we have a potential VBE. Then I see RE, through which a current IE will be flowing. So we have a potential drop IE-RE across it. Further, I go back to the ground. If you look at R2, current flowing through it is actually flowing in this direction. That means it has a positive potential here and negative potential here. VBE has positive here and negative here. Since IE is flowing through RE in this direction, that must mean RE has a positive potential here and negative potential here. Now, VB, which is the potential drop on the resistor R2, is from negative to positive. VBE is from positive to negative. IE-RE also from positive to negative. So, if we apply Kirchhoff's voltage law, we get VB minus VBE minus IE-RE is equal to 0. We know VB is 4.7 volt. It is given in the question VBE is 0.7 volt. RE is also given, it is 2 kilo ohm. So we can easily find out what is IE. The value of IE is 2 milliampere. Further in the question it is given that the base current is negligible, which means emitter current is equal to the collector current. So we get the value of the collector current, it is 2 milliampere. Now let's bring the gain. It is negative GM RC parallel to RL. And GM is IC by VT, so I will write it that way. Magnitude of gain is IC by VT multiplied by RC parallel to RL. We have all the values, so let us give the values. IC is 2 milliampere, VT is 25 millivolt. RC is 2 kilo ohm and RL is 8 kilo ohm. Equivalent resistance of 2 parallel to 8 will be 2 multiplied by 8 divided by 2 plus 8. Doing the calculation, we get the gain, it is 128. And that's our final answer. Let us see the next problem. In the figure given, the NPN transistor acts as a switch. The input Vin as a function of T is shown over here in the graph. The transistor switches between the cutoff and saturation regions of operation when T is large. We can assume that the collector to emitter voltage at saturation is 0.2 volt and base to emitter voltage is 0.7 volt. What we have to find out is the minimum value of the common base current gain alpha of the transistor for the switching. But the question is to find the minimum value of common base current gain. Alpha is minimum in the saturation region. So we have to find out the values of IC and IE in saturation region. We also know IE is actually IC plus IB. So basically we have to find out IC and IB. Let us start by calculating the value of collector current at saturation because alpha is minimum at saturation. It's already given in the question that the collector emitter voltage at saturation is 0.2 volt. Now, collector current is the current that flows through the collector resistor, which over here is 4.8 kilo ohm. If you take a look at this resistor, you can see on one end it has plus 5 volt. On the other end, it has VCE. It is given in the question VCE at saturation is 0.2 volt. So the resistor has plus 5 volt here and 0.2 volt here. So the collector current at saturation will be 5 minus 0.2 divided by 4.8 kilo ohm. And this comes out to be 1 milliampere. Again, alpha is IC divided by IE. We have IC, now we have to find out IE. IE is IC plus IB. So what we have to find out right now is the base current IB. For that, we'll apply Kirchhoff's voltage law in the base emitter loop. I'll start from this point and go clockwise. First, I have V input from negative to positive. As I go on, I have the 12 kilo ohm. Current through 12 kilo ohm is the base current and that flows in this direction. That means the 12 kilo ohm will have positive potential here and negative here. As I further go on, I have the base emitter junction, positive here, negative here. Current flowing through the 12 kilo ohm is the base current IB. So the potential across it is 12 kilo multiplied by IB. Now applying Kirchhoff's voltage law, I can write V in minus 12I minus VBE is 0. Let's give values. From the graph over here, we can see that V in is 2 volt. It is given in the question VBE is 0.7 volt. So by substituting the values, we get IB and it is 0.108 milliampere. Why is it milliampere? Because 12 is in kilo ohm. Finally, we have IC and IB. So let us find IE, which is their sum. So IE is 1.108 milliampere. Now, the minimum value of alpha is the collector current at saturation divided by the emitter current. Giving the values, we get 0.902 and that is our final answer. Let us see the next problem. In the circuit given, transistors Q1 and Q2 are biased at the collector current of 2.6 milliampere. Now, assuming that the transistor current gains are sufficiently large to assume collector current is equal to the emitter current and thermal voltage is 26 millivolt. What we have to find out is the magnitude of voltage gain V out by V source in the mid-band frequency range up to second decimal place. If you simply take this much of the circuit, you can see that it is simply a common emitter amplifier. Input is given at the base, output is taken at the collector. Usually for emitter degeneration, we give a resistance over here. Instead of that, we have this whole circuit. So all we have to do here is to find out the equivalent resistance of this circuit when seen at this terminal of the transistor Q2. Once we find that, we can consider that as the resistance we have at the emitter of the common emitter amplifier and find the gain accordingly. So to find the equivalent resistance of this part, I will take that out. To make it look normal to us, I am going to flip it vertically. This is the emitter terminal of the transistor, so we have to find out the resistance seen at the emitter. For that, the first thing we need is the small signal model. But before we do that, let us acknowledge the fact that this is not an NPN transistor, it is a PNP transistor. The small signal hybrid pi model of a PNP transistor looks like this. The difference is direction of GM Vpi is opposite. Vpi will also have opposite polarity. Now collector gets minus 5 volt, which in the small signal analysis will be the AC ground. So collector can be grounded. From the base to the collector we have RB2. So in the small signal model it will be between the base and the AC ground. We also have a capacitor between the base and the ground. In the small signal model we only have AC signals, so the capacitor can be considered a short circuit. But in that case, the base will be directly grounded. Now, this is the most important thing you can see right now. Take a look at RB. Its one end is connected to the ground. The other end is also connected to the ground. So basically, RB is shorted. So even if you remove RB, nothing is going to happen in the circuit model. So let us remove it. Now comes the real action. All we have to find out is the resistance when looked through the emitter. So we have to add a potential Vx over here and find its relation with Ix, which will be the current flowing over here. Let us start by applying Kirchhoff's voltage law in the base emitter loop. I'll start from this point and go clockwise. First I see Vpi from negative to positive. Then over here I have Vx from positive to negative. Then I go back to the ground. So I can write Vpi minus Vx is equal to 0 or Vpi is equal to Vx. Now let us apply Kirchhoff's current law at the emitter node. We have three currents. Ix is flowing into the node. GMVpi is flowing out of the node. There will be another current flowing through Rpi in this direction because Vpi has positive potential here and negative here. The current will be Vpi by Rpi. Two currents are going out of the node, one is coming into the node. So we can write Vpi by Rpi minus Ix plus GMVpi is equal to 0. These two are positive because they are going out of the node. This is negative because it is coming into the node. Now we got Vpi is Vx. So we can write Vx by Rpi minus Ix Gm Vx is equal to 0. What we want is the relation between Vx and Ix. Specifically Vx divided by Ix. Rearranging this equation, we get Vx multiplied by 1 by Rpi plus Gm is Ix, or Vx by Ix is 1 by Rpi plus Gm. Now 1 by Rpi will be a very small number compared to Gm. So when we take the sum 1 by Rpi plus Gm, we can say this is approximately equal to Gm itself. That makes Vx by Ix approximately equal to 1 by Gm. So technically, to find the gain of this circuit, we can replace this whole thing and model it as a resistor at the emitter of the first transistor, and the value of the resistor will be 1 by Gm. Like this. Now what we have over here is just a common emitter amplifier with emitter degeneration, and there is no bypass capacitor. In such a case, we can write the gain to be minus RC divided by 1 by Gm plus RE. Here RE is also 1 by Gm, so in the denominator we get 2 by Gm. Gm is IC by Vt. Value of IC is given in the question. Vt is also given. RC is 1 kilo ohm. So all we have to do is substitute the values. If we do that, we get that the gain is minus 50. But the question is to find the magnitude of voltage gain. So our final answer will be 50. Before we go to the next problem, I want to discuss something called diode connected load. It is basically a BJT with its base and collector shorted. Something like this. I have taken an NPN transistor. If I draw the small signal model of this connection, this is how it will look like. If I draw the small signal model of this connection, this is what I get. Base and collector are directly connected to each other. Since there is no resistance at the collector, collector goes to the AC ground. Now, what I want to find out is the impedance of this circuit when seen at the collector. For that, all I have to do is take the small signal model, apply a potential Vx at the collector and find its relation with the current Ix that will be flowing over here. Vx is directly connected across R pi. So V pi is equal to Vx. Now let us apply Kirchhoff's current law at the collector node. I can see three currents. Ix is flowing into the node. GMV pi is flowing out of the node. The third current is the current that flows through R pi, and it will be in this direction because V pi has positive here and negative here. And the current will be V pi by R pi. So we can write Ix is equal to V pi by R pi plus GMV pi. But V pi is equal to Vx. So we can write the right hand side of this equation like this. Vx multiplied by 1 by R pi plus Gm. Now to get the impedance, what we want is Vx by Ix. From this equation, we can write Vx by Ix is 1 by R pi plus Gm. Again, 1 by R pi will be a very small value compared with Gm. So 1 by R pi plus Gm can be approximated to just Gm. That means Vx by Ix is approximately 1 by Gm. So the diode connected load is equivalent to a resistor of resistance 1 by Gm. This is called the diode connected load because when the base and collector are shorted, the transistor acts as a diode. So when you see a diode connector transistor in a circuit, you should be able to model it as a resistor whose resistance is 1 by Gm. Let us now take a look at our previous problem. Obviously, what we have over here is not a diode connector transistor because the collector is not directly connected to the base. There is a resistor in between. But we also have a capacitor over here. The capacitor will be short circuited in the small signal model. That will make the base directly grounded. But that will make the base resistance short circuited. We even removed RB from the small signal model when we solved this. Now with RB being shorted, what we have over here will technically become a diode connector transistor. Without RB, what we have over here is exactly the small signal model of a diode connector transistor. Here both base and collector are connected to the ground. So technically they are connected to each other, which means the base and collector are shorted just like a diode connector transistor. But there is one difference. We are taking the resistance seen through the emitter. Because over here in this circuit, the emitter is what is connected to the common emitter amplifier's emitter. But still, I took its equivalent resistance to be 1 by Gm. Why? Don't worry about it, because I didn't just take it. I did the small signal analysis and showed you it is 1 by Gm. So what I'm trying to tell you is that this problem shouldn't have taken us that much time to solve. Once you understand that RB is being shorted by the capacitor, you should be able to recognize there is a diode connected load and replace it with a resistor of resistance 1 by Gm. Once you do that, the problem should be solved well under 60 seconds because the only thing that is left is simple mathematics. Let us move on and see the next problem. The Miller effect in the context of a common emitter amplifier explains. Option A says an increase in the low frequency cutoff frequency. Option B says an increase in the high frequency cutoff frequency. Option C says a decrease in the low frequency cutoff frequency. And option D says a decrease in the high frequency cutoff frequency. The basic thing about Miller effect in the context of a common emitter amplifier is that it comes into action at high frequencies. So obviously option A is not the right answer, option C is also not the right answer. The only thing we have to figure out is if it increases the cutoff frequency or if it decreases the cutoff frequency. For that we have to know what Miller effect does. Miller effect significantly increases the input capacitance. And cutoff frequency due to the input RC circuit is 1 by 2 pi R in C in. which means the upper cutoff frequency is inversely proportional to the input capacitance. So, since Miller effect increases the capacitance, it decreases the upper cutoff frequency. The correct option is option D. Let us see the next problem. Consider the circuit shown in the figure. Assume base to emitter voltage is 0.8 volt and the common base current gain alpha of the transistor is unity. What we have to find out is the value of the collector to emitter voltage in volts. Here the first thing is alpha is unity. We know alpha is IC divided by IE. If alpha is 1, that means IC is equal to IE. If collector current is equal to emitter current, then base current is technically 0. Let it be there. Let's see the circuit. Over here we have the voltage divider bias. To make the analysis simpler, I am going to use the Thevenin equivalent of the voltage divider. We have 44 kilo ohm and 16 kilo ohm. So the Thevenin equivalent resistance will be 44 multiplied by 16 divided by 44 plus 16. Thevenin equivalent voltage will be whatever is the voltage that drops across the 16 kilo ohm resistor. To find that, all we have to apply is voltage division. So Thevenin voltage becomes 18 volt, which is the VCC, divided by 44 plus 16 multiplied by 16. This comes out to be 4.8 volt. Let us redraw the circuit like this. The voltage divider is replaced with its Thevenin equivalent. This will make the analysis easier. Let us start by applying Kirchhoff's voltage law in the base emitter loop. I'll start from this point and go clockwise. So I have VTH. As I go on, I have RTH through which a current IB will be flowing. So the potential across it is IB RTH. Since IB is flowing in this direction, positive here and negative here. As I further go on, I have the base emitter junction across which VBE will be dropped. Then I have the 2 kilo ohm resistor over here through which IE will be flowing. Since IE is flowing in this direction, potential across this resistor will have positive here and negative here. So I can write VTH minus IBRTH minus VBE minus IE multiplied by 2 kilo ohm is equal to 0. We know the value of VTH, it is 4.8 volt. We found IB to be 0. VBE is given in the question 0.8 volt. RE is also given 2 kilo ohm. Let us substitute all the values so we get the value of IE. IE comes out to be 2 milliampere. But IE is equal to IC, so IC is also 2 milliampere. Now what we have to find out is the collector to emitter voltage. That is the voltage drop over here. To find that, all we have to do is apply Kirchhoff's voltage law in the collector emitter loop. Because we are applying 18 volt here, out of that ICRC will be dropped over here. IERE will be dropped over here. And the rest has to be dropped between the collector and emitter. So VCE will be VCC minus ICRC minus IERE. We have all the values. VCC is 18 volt, IC is 2 milliampere, RC is 4 kilo ohm, IE is also 2 milliampere, RE is 2 kilo ohm. So by substituting the values, we see that VCE is 6 volt. So the final answer is 6. Let us see the next problem. Resistor R1 in the circuit is adjusted such that I1 is 1 milliampere. The transistors Q1 and Q2 are perfectly matched and they have very high current gain so that their base currents are negligible. Supply voltage is 6 volt and the thermal voltage Kt by Q is 26 millivolt. What we have to find out is the value of R2 in ohms, for which I2 is 100 microampere. Let us see how we can figure this out. We'll start by applying Kirchhoff's voltage law in this loop. I'll start from this point and go clockwise. The first thing I can see is the first base emitter voltage from negative to positive. Then I have the second base emitter voltage from positive to negative. Then I'll have the potential drop across R2. Since current will be flowing in this direction, R2 will have a potential, positive potential here and negative here. Now, it is given in the question that the base currents are negligible. So, if I2 is the collector current of the second transistor, I2 will also be its emitter current. That means the potential drop across R2 will be I2R2. Now, if I apply Kirchhoff's voltage law, I can write VBE1 minus VBE2 minus I2R2 is equal to 0. From this, I can write an expression for R2. R2 is VBE1 minus VBE2 by I2. We already know the value of I2. It is supposed to be 100 microampere. So all we have to find out so that we get the value of R2 is the difference between VBE1 and VBE2. We know base emitter voltage is given by the expression Vt log of Ic by Is. So VBE1 will be Vt log of I1 by Is and VBE2 will be Vt log of I2 by Is. What we want is VBE1 minus VBE2. So that will be Vt multiplied by log of I1 by Is minus log of I2 by Is. Now, log of x minus log of y is log of x by y. Here, if you divide I1 by Is with I2 by Is or multiply with Is by I2, Is and Is will get cancelled and we get I1 by I2. So this entire thing simply becomes log of I1 by I2. Let us substitute that over here in this equation. That gives us R2 is Vt log of I1 by I2 divided by I2. We have all the values. Vt is 26 millivolt, I1 is 1 milliampere, I2 is 100 microampere. If we give the values, we get R2 is 598.67 ohm. So the final answer is 598.67. Let us see the next problem. Which one of the following statements is correct about an AC coupled common emitter amplifier operating in the mid-band region? Option A says the device parasitic capacitances behave like open circuits, whereas coupling and bypass capacitances behave like short circuits. Option B says all the capacitances behave like open circuits. Option C says all the capacitances behave like short circuits. Option D says parasitic capacitances behave like short circuits and coupling and bypass capacitances behave like open circuits. Let's figure this out. Let us start by taking the capacitive reactance of coupling and bypass capacitors. Capacitive reactance is 1 by omega C. Here the amplifier is operating in mid-band region, so the frequency is neither too low nor too high. Since we are dealing with coupling or bypass capacitor, capacitance is also on the higher side. So 1 by omega C will be too small so that we can short them. Now, when it comes to the parasitic capacitances or the junction capacitances, if we take the reactance 1 by omega C, omega will have the same value, but capacitance is going to be really small when compared with coupling or bypass capacitors. That will make the denominator too small, making the reactance too high. If the reactance is too high, that means we'll have to open the circuit. Option A is correct. Let us see the next problem. Consider the circuit shown in the figure. Assuming VBE1 and VBE2 are 0.7 volt, we have to find the value of DC voltage VC2 in volt. Let us apply Kirchhoff's voltage law in this loop. Is this really a loop? Yes, if you consider VCC like this, let's say we have a cell of 2.5 volt, goes back to ground, right? So this is a loop. I'll start from this point and go like this. So I have VCC. As I go on, I have VBE1, then I have VBE2, Then I have potential drop across the 10 kilo ohm resistor. Then I have a 1 volt and I go back to ground. If I take VCC like this, I can see VCC is from negative to positive. VBE1 is from positive to negative. VBE2 is also from positive to negative. Why? Because this is a PNP transistor. Now, current flowing through the 10 kilo ohm resistor will be base current of the second transistor. Since it is a PNP transistor, base current's direction will be like this. That means 10 kilo ohm will have positive potential here, negative here. Let us also show the base current IB2. Finally, we have a 1 volt also from positive to negative. So if we apply Kirchhoff's voltage law, we'll get VCC minus VBE1 minus VBE2 minus 10 kilo multiplied by IB2 minus 1 volt is equal to 0. What are the values we have? VCC is 2.5 volt. VBE1 and VBE2 are 0.7 volt. If we give the values, we can find the value of IB2. IB2 comes out to be 0.1 divided by 10K or 0.01 milliampere. Let me tell you why I need IB2 first. The question is to find out the value of VC2, which is the potential taken over here. VC2 is the potential drop across the 1 kilo ohm resistor. But the 1 kilo ohm resistor is actually at the collector of this PNP transistor. So the current flowing through the 1 kilo ohm resistor will be its collector current, IC2. If I know IC2, then VC2 will be IC2 multiplied by 1 kilo ohm. But I don't know IC2. So I found IB2. Because IC2 will be beta times IC2. And beta is given in the question. It is 50. So IC2 is beta 2 times IB2. Beta 2 is 50, IB2 is 0.01 milliampere. So IC2 is 0.5 milliampere. So current flowing through the 1 kilo ohm resistor is 0.5 milliampere. That means the potential across it is IC2 multiplied by 1 kilo or 0.5 milli multiplied by 1 kilo, which is 0.5 volt. So the final answer is 0.5. Let us see the next problem. In the AC equivalent circuit shown, two BJTs are biased in active region and they have identical parameters with their current gain being very much greater than 1. What we have to find out is the open circuit small signal voltage gain. The first and the most important thing, do you see anything familiar in this circuit? What we have over here is a transistor whose base and collector are shorted. It is a diode connected load. We already learned it is equivalent to a resistance of 1 by Gm. So basically here we have a transistor who has a resistance 1 by Gm at the collector. Input is given at the base, output is taken at the collector. So this is a common emitter amplifier. Gain of a common emitter amplifier is minus Gm RC. Here RC is 1 by Gm. That means the gain is minus 1. Let us see the next problem. In the circuit shown, I1 is 80 milliampere, I2 is 4 milliampere. Transistors T1 and T2 are identical. Assume that thermal voltage is 26 millivolt at 27 degrees Celsius. What we have to find out is the value of the voltage V12, which is V1 minus V2 at 50 degrees Celsius in millivolts. Let us start by applying Kirchhoff's voltage law in this loop. I'll start from the ground. I have the base emitter junction. Then I go through here. Then I have a V12. I go through here. I have another base emitter junction. And I go back to ground. I'll start from this point and go clockwise. VBE2 is from negative to positive. As I go on, I have V12 here. It is also from negative to positive. Further as I go on, I have VBE1. It is from positive to negative. Then I go back to ground. So if I apply KVL, I can write VBE2 plus V12 minus VBE1 is equal to 0, or V12 is VBE1 minus VBE2. So to find V12, all we need is the difference between VBE1 and VBE2. We already did that in one of our previous problems. Since VBE is VT log of IC by IS, we can write VBE1 and VBE2 as VT log of I1 by IS and VT log of I2 by IS. If we take the difference, we get VT times log of I1 by IS minus log of I2 by IS, which becomes log of I1 by I2. Here I1 is 80 milliampere, I2 is 4 milliampere. So I1 by I2 becomes 20. But there is one problem. What will we take as the value of VT? It is given in the question VT is 26 millivolt at 27 degrees Celsius. But the question is to find the voltage V12 at 50 degrees Celsius. So we have to find out the value of thermal voltage at 50 degrees Celsius. It is easy because we know Vt is Kt by Q. K is a constant, Q is a constant, so thermal voltage is proportional to the temperature. But one thing to keep in mind is we have to take temperature in Kelvin. So at 50 degrees Celsius, thermal voltage will be 26 millivolt divided by 300 Kelvin, which is 27 degrees Celsius, multiplied by 323 Kelvin, which is 50 degrees Celsius. Now we can use this to find Vt log of I1 by I2, which is equal to VBE1 minus VBE2, which is equal to V12. So V12 becomes 26 divided by 300 multiplied by 323 millivolt multiplied by log of 20. This comes out to be 83.86 millivolt. So the final answer is 83.86. Let us see the next problem. In the circuit shown in the figure, the BJT has a current gain of 50. The emitter base voltage VEB is 600 millivolt. What we have to find out is the emitter collector voltage in volts. From the figure, you can see that we are applying a 3 volt over here at the emitter. Out of that, IC multiplied by 500 ohm will be dropped over here. Whatever is the rest will be dropped between the emitter and the collector. So to find the emitter collector voltage, what we need is IC. But to find IC, we need IB because IC is beta IB. Now to find IB, we need the potential over here, VB. Let us see how we can do it. It is given in the question VEB is 600 millivolt. Or we can write it is 0.6 volt. Now VEB can be written as VE minus VB. So VE minus VB is 0.6 or VB is VE minus 0.6. Now what is VE? From the circuit diagram we can see that at the emitter we have a 3 volt supply. So VE is 3 volt, that means VB is 2.4 volt. So at this point, which is at the base, we are getting a 2.4 volt. Here we have 0. In between we have a resistor of resistance 60 kilo ohm. So we can easily find out what will be the base current flowing through it. It is 2.4 divided by 60. IB will be VB divided by 60 kilo ohm or 2.4 by 60 kilo ohm, which is 0.04 milliampere. Now that we have IB, we can find IC because current gain is given in the question. IC is beta IB, so it is 50 times 0.04 or 2 milliampere. Now that we have IC, we can find out what is the collector emitter voltage. Because over here we are giving 3 volt. Out of that 500 IC will be dropped across the 500 ohm resistor. The rest will be dropped between the collector and emitter. So first let us find out the potential drop across the 500 ohm resistor. It is ICRC. IC is 2 milliampere, RC is 500. So this becomes 1 volt. So we have 3 volt here Out of that, 1 volt is dropped across this resistor. The rest of it will be dropped between the emitter and the collector. So we get VEC is 3 minus 1 or 2 volt. So the final answer is 2. So that's all about it for today. See you in the next video. And please don't forget to subscribe.